Alright, here we are on page 2. It says given the following function, it's a third degree polynomial. We could write this as 1/3 x to the third plus x squared minus 3x plus 1. And it might be a little bit easier to see that they've made it so that the derivative is pretty handy. Anyway, find all local maximum and minimum values. Well, the third degree, in which the first term is positive, is going to have this simple curve going like this. So you could sketch a little thumbnail of it just to get an idea, a little rough draft, without using your calculator at all on this one. And you know it's going to go like this. So it's going to have one local maximum, one local minimum, and we're going to find that by taking the derivative, as we have done many times before, and set that equal to 0. So take the derivative of this, and you bring the 3 out, and you get f prime of x then is equal to x squared plus 2x minus 3. Well, we're going to set this equal to 0 then, and lo and behold, it factors easily. How nice. X plus 3x minus 1. If you didn't know that, you could toss it into quad form and you'd find it. Well, that's going to be equal to 0 when x is equal to -3 and positive 1. So we know that this is going to happen when x is -3, right there, and positive 1. And then the actual value when x is -3, if I plug in -3, that's -27, but then taking that divided by 3, f of -3 will be equal to -9 plus 9, because -3 squared, and then plus 9 again, plus 1. These cancel and I get 10. So I'm going to go -3 and up to 10. That's my maximum value. -3, 10. Label that. And then f of positive 1 should be straightforward enough. That's 1/3 plus 1 minus 3 plus 1. So that's 1 and 1 is 2. That's -1. So that's -2/3. -2/3. And so when I'm at positive 1, I'm down right there, -2/3. So this is going down like that. This is going to go up like that. I can plug in 0 and I get plus 1, so I know it's going to go through right there. And I'm just going to sketch it going up like that, going down like that, going down like that. That is pretty good right there. Now it says find the points, find all the intervals on which the function is increasing or decreasing. Well, here it's increasing from infinity to -3, and it's not including those points. And it's increasing from positive 1, to positive infinity. This is increasing. Decreasing then is only from -3 to positive 1. And I've got the soft brackets there because it does not include those actual maximum points. Find all points of inflection. It's only going to have one point of inflection right there because it's concave down on either side and then concave up other side. So I take the second derivative. So I go back to this and I find the second derivative. I'll move that up a little bit just so I can show it here. F double prime of x is equal to then 2x plus 2. Well, I set that equal to 0 as well, and that's going to be equal to 0 when 2x equals -2 or x equals -1. So that makes sense. I just happen to draw that right above the -1, and if I plug that in to my original function, the point of inflection will be at f of -1, which will be -1/3, and then plus 1, and then plus 3, and then plus 1. So that's 5 minus 1/3. So that's 4 2/3. Okay? So I have then found the points of inflection, identify the intervals on which the function is concave upward. So I'm going to write that here. concave up, CU, that's from negative infinity to negative 1. And it's concave down, concave down, CD, is from negative 1 to positive infinity. Okay, I got interrupted there, but I think I'd finished that problem. Number 5, a large open-top shipping container with a base that's twice the length as its width. We did this in class, so I'm going to kind of go through it more quickly, but if we have this container and its footprint, as they say, is 2 to 1, x to 2x, and there's some unknown height, then we can figure out the volume based on the fact that it's going to be length times width times height, or x times 2x times h, which will be then a volume of 2x squared h. Well, the surface area, we know we're allowed to have a surface area of 1,200 feet. That surface area is going to be equal to the front times 2, because there's a front and back. So that's x times the height, h, times 2. And then this side right here times its opposite one back there. That's going to be 2x times h. And then times 2, I guess I'll put another 2 there. And then finally just the bottom is going to be x times 2x, or 2x squared. So to simplify that, that's going to be 2xh, and 4xh is 6xh plus 2x squared, and that's going to equal our total of 1,200 square feet. Well, if I solve for just h will be equal to 1,200 minus 2x squared divided by 6x, and I can cancel a 2 everywhere and then get a 3 and change that into 600, and then minus x squared. So here I'm going to take this equation and replace h with what it's equal to. So I'm going to scribble out the h. Well, actually I'll rewrite it so when I make a photocopy it's not too messed up. 2x squared times then 600 minus x squared all over 3x. Okay? If I cancel this x with that x and then multiply in by 2x, I'll get the volume is equal to 1200x minus 2x squared, and then all over 3, which in class I guess we made 400x minus 2/3 x squared. So that is the function that is my volume. Now I take the derivative of that. I'm doing this all in about a postage stamp size, but v prime is equal to then 400 minus, when I bring the 2 in, that's going to be minus 4/3 x squared. And I am trying to set that equal to 0, so I'm just going to work down here. Setting that equal to 0, 400 then will be equal to 4/3 x squared. Multiply both sides by 3/4, and I get 300 equals x squared, and x is equal to the square root of 300. I remember in class that it was 200, but unless I made a mistake, that's correct. So turning this on and then taking the square root of 300, I get 17.3. So x is 17.3, approximately 17.3, and this is twice that, so that's 34.6. And then plugging in our original formula, I could find out h. I guess I'll let you do that on your own. I'll write it, and it'll be on the photocopy that I post in Moodle, but I'm not going to do it here. Finally, this last one is f of x is equal to x over x squared plus 25. Find the derivative of f of x and then graph that function on the calculator. Okay, using this graph on the calculator to determine the maximum and minimum points of this original function and where it is increasing or decreasing. Okay, so f prime of x then is going to be, well, I like rewriting this in the form of x times x squared plus 25 to the minus 1. So when I take the derivative, it's going to be this times the derivative of that plus that times the derivative of this. It's just my product rule. So this times the derivative of that will be x times then minus and then x squared plus 25 to the minus 2. When I take away 1, bring the negative 1 out in front, there it is, to the minus 2, then times the derivative of the inside, which is 2x, and then plus this times the derivative of this, which is just x squared plus 25 to the minus 1. Now, cleaning this all up, I've got this underneath being squared, so that's going to be on top. It's going to be negative 2x squared, x times x, 2x squared, over then x squared plus 25 squared, and then plus 1 over x squared plus 25. That's the derivative. That's f prime of x. And then I'm going to graph this function on my calculator. So let me put that into the calculator. Okay, here's the last little bit. The thick line is the derivative. Now I cleaned up the derivatives while I turned off the camera, and I just took that 1 over x squared plus 25, and then I multiplied top and bottom by x squared plus 25. It got me a common denominator, and then when I added the first part plus this second part, because remember I multiplied top and bottom by x squared plus 25, this minus 2x squared and the plus 2x squared became minus x squared, and I just wrote it like this. So this is the all-important numerator, because I'm really wondering, when is this equal to 0? And this is equal to 0 when x is plus or minus 5. So to answer this question, using the graph in the calculator, actually I'm using calculus here, determine the max and minimum points of this original function. Well, that's going to happen. The max and min is going to be at, and you can see it here in the calculator, it's going to be the maximum's at positive 5 and the minimum's at negative 5. Is at 5, and the minimum is at negative 5. Okay? And there's the graph. So, hope that helps.